Hello and welcome. My name is Visser and I'm a senior principal engineer at CONFLUENT, and it's my honor and privilege to be talking to you about running Apache Kafka at scale in the cloud. Now, personally, I'm very excited to talk about this topic because in the past 30 years, I've seen a lot of data architecture happen in front of my eyes. When I started working, I was a system programmer on a mainframe, and there'll be a picture of that later. And then we moved to relational databases and client-server applications. And now in the last 10, 15 years, I've been working on massively scaling applications using event streaming and NoSQL. So there's a lot has happened in our industry in the last couple of years. And I'm really excited to be talking about one of the most hot topics at the moment, which is event streaming. So these are topics that I can talk about for days, but we only have a very short amount of time. So we have to limit sort of what I'm going to talk about. So what we'll cover is a short introduction to Kafka. Then I'll go into the challenges of scaling Kafka for a particular workload. Then I'm going to spend a few words on Confluent's core business, which is running Kafka in the cloud, and then the various challenges that brings with it. And then last but not least, I have some parting words, and by that time, I will have already wasted some of your time, and I have references to more material on Kafka and scaling Kafka. So let's start with what is Kafka. And the reason I wanted to spend a few words on that is that this presentation doesn't make a lot of sense if you have no idea what Kafka is. So hopefully it won't be too boring for the people who already know Kafka. So let's start with the past. This was the past. The past was big and red, or big and blue. This is an IBM mainframe. When I started working, as I said, I was a system programmer at a bank, and we had 4 computers at the bank, 3 of which were for running production, and 1 was our test mainframe. And in that environment, it is not hard to know where your data is and where it is needed. It can only be in 1 of 3 places, and it's typically very easy to find and very easy to get at. That is not the problem we have today. If you look at the world today, it looks more like this. 3 boxes. People buy applications, buy databases, write applications, use databases, and obviously they need to exchange information. You see the arrows here, which are like an indication of data flowing from application to application. But as companies grow and they get more infrastructure, more applications, more databases, they also get more silos of data that all manage to maybe exchange some data with each other. But then if you look at the company as a whole, what you will see is that what you need is your data flowing, but what you have are data stores. And so the problem that many companies have is exactly this, like data from one silo needed in another silo in order to send out SMS messages, give emails, react, produce linear boards, like for whatever business reason you can imagine, there's always a need for data at a particular location where it's not, coming from a location where it's at that has no idea on how to get it where it needs to be. And each of the arrows that I have on this slide presents a problem. It presents a security problem, it presents a technical problem, it presents a data typing problem, it presents a latency and throughput problem. And for each of these arrows, you need to solve this problem again and again. And the other bad thing about this picture is that as you grow your infrastructure and you introduce more applications and more databases, the number of arrows grows exponentially, making the problem harder and harder to solve. So this is obviously not the way. Then you ask me, Jas, you ask me, what is the way? Well, this is the way. Like, instead of having all these arrows going from here to there, we introduce a centralized event streaming platform, a place where applications that produce data that is of interest to the rest of the company can deliver it and store it temporarily, and people that are interested, or applications that are interested in that data, can read it out of that event stream and process it, and then maybe write some new data back into it that then gets processed by other people. So instead of having tons of arrows going from here to there, you sort of have a centralized place where you sort of deliver all the data that is of interest to anyone else, and out from there on out, it goes to places that it's needed. And the beauty of such a centralized infrastructure is that you now have a single place where you solve all of these problems that I just mentioned. You have like a single place where you solve the security problem, the latency problem, the throughput problem, the data typing problem, the whatever problem you have that is involved or comes up when you start sending data around. You now have sort of one place where you can solve that problem. So this is why tons and tons of companies are using event streaming this way. Now, other presentations that you may hear in this conference are about FOQS, which is Facebook's pub subsystem, and you may have heard of other applications like MQ Series and RabbitMQ. They all play sort of in the same space. Now, this is not the right time to give for the point-by-point feature comparison between all of these products, but they play in the same space. Kafka is like an extremely popular solution for solving event streaming and for solving the problem of sending data from one application to another, even though the application that produces the data doesn't know which applications use it. So in a nutshell, Kafka is a platform that is oriented around real-time streams of data. And so applications can produce data into the platform where it will be stored and it's ordered and timed, and there's all sorts of other goodness and secured. And applications that are interested in the data can consume it out of the platform. The beauty of Kafka is that it scales linearly to data volumes, but there's something to say about scaling, which we'll get to in the next section. One of the great things about Kafka is that it's also a storage system. So it's not just a transient sort of pipeline of data, but you can store data in Kafka and then later query it from there. And we have a SQL-like language that allows you to do that. We have standardized connectors. We have over 100 connectors for storing and retrieving data in and getting them from standard applications and databases such as Oracle, MySQL, Postgres, but also like Salesforce, Snowflake, and a bunch of others. So if you use one of these standard applications or databases, you don't need to write Kafka or code, Kafka library code in order to access that. We have connectors for that. Kafka contains a very powerful stream processing library that allows you to write your own applications in a modular fashion, in a multitasking, multi-processing fashion that allows you to write very high performance event streaming applications. And there's a side product of the platform called KSQLDB, which allows you to create new data from existing data streams using a SQL-like language. And that's a very popular feature for writing or creating new data streams and data feeds based on existing data streams without actually writing a lot of code. A few lines of SQL, if you'd like to call that code. So in the picture, here's your data. At the center consists of like event records. They're split in partitions. That data lives on a set of brokers, which are processes on computers that maintain, manipulate, store, read, right, like that are responsible for managing that data. You write applications that produce and consume that data, or you can use one of our standard connectors in order to connect to existing and standardized and well-known applications and databases. And at the end, if you want to, you can write your own applications in SQL or a SQL-like language using KSQLDB to join streams, to create new streams, filter streams, and do other sorts of advanced data manipulation. So I hope that gave sort of a good overview of Kafka. Now let's talk about scaling Kafka, because like I said, Kafka scales linearly with your data volume, but there's always sort of things to be improved. And then one of the good things about Kafka is that its internal architecture has been designed to facilitate automatic scaling. So that means that Kafka internally uses a lot of the standard techniques that are well known in our industry for making sure that the application scales, or the Kafka cluster scales with your amount of data. And so it automatically distributes data across multiple brokers. Brokers use zero copy transfer to send data on its way, so there's no time wasted in copying data around. Consumers are automatically balanced across all of the brokers. State stores are automatically backed up. Leadership is automatically determined when one of the computers fails. And so there's a lot going on in Kafka internally that ensures that that Kafka out of the box does a very good job of dealing with everything you throw at it. And so the text on the slide is a quote from our Optimizing Your Kafka Deployment white paper. The URL is at the bottom of the slide, and it contains a wealth of information on like how Kafka works and what you can do to optimize it for particular scenarios. Because even though Kafka scales really well under its default configuration. There are always scenarios where you need to tune Kafka for your particular workloads, because scaling always happens over a dimension, and you need to know which dimension you're interested in. And unfortunately, in Kafka, like in databases and like in the real world, you can't have your lunch and eat it at the same time. So you have to make some choices, and sometimes choosing to optimize along one dimension sort of diminishes your results along another dimension. But there's nothing we as engineers can do about that. You need to sort of complain to the person who created the universe and the laws of physics, because that is what sort of warrants this sad result. The four dimensions I'm going to talk about are throughput, latency, durability, and availability. Talk about throughput. So throughput is the dimension where you send as much data through Kafka as possible. And optimizing for throughput often comes down to hurting individual message latency, because throughput happens from batching, by waiting for messages to come in and handle them as a batch instead of as individual messages, thereby leveraging a lot of the sort of common code that goes on in message processing over all of the messages in the batch. And so one of the other things you want to do there is make sure that you hear back from the Kafka cluster as soon as the broker has the data, which is achieved by the X variable or the X property, maybe. By setting it to 1, you make sure that you get a commit back from the broker as soon as one broker has the data, which is great for throughput because it means you can start sending the next batch. But as we will see later, it does hurt durability. The other thing we can optimize for is latency. And latency is typically about individual message responses. And so it's in many ways, it's the opposite of throughput. Latency is you don't want to wait for batches, so you want to set linger to 0. You want to disable compression because that takes time. You want to again set the number of acknowledgements to 1, making sure that you hear back from the broker as soon as it got the data. And that means that as soon as a message arrives, it doesn't wait for any batching, doesn't compress, immediately sends it to the broker. Broker deals with it, immediately sends a response back, and thereby ensuring that you have optimal response time on that single individual message. The third axis of scalability I want to mention is durability. And durability is all about, is my data safe? If I hear back from the Kafka cluster that it has the data, how safe is my data there? And the answer to that is replication. Like Kafka uses replication internally to make sure that your data is safe. But the question here is, if you send your data to the Kafka broker and you hear back from it, how many replicas have it by then? And that is, again, this is the third time I'm talking about the X property. If you set X to all, you make sure that by the time you hear back from the Kafka cluster, all of the replicas have the data. And that means that even if the broker that you were just talking to sort of burns to a crisp and the hard disk is gone and it's never heard from again, the replicas have the data. And the way they have the data is such that the ordering and all sorts of other good things are guaranteed. Obviously, this slows things down, right? Because you have to send the message, it's replicated out, wait for the acknowledgements of the replica to get to the leader, then the leader has to respond to you. So you get a lot of safety, but at the cost of performance. And that is one of the reasons why you can't have your cake and eat it, why you can't optimize for all of these dimensions at the same time. And if you look at the X property, which we advise to set to all for this particular use case, you can immediately see that this contrasts with the other two use cases for latency and throughput, where we advise to set it to 1. The last scalability dimension that I want to talk about and discuss is availability. And that is, how available is the cluster for you to take your calls? The problem there is that Kafka gives a lot of guarantees about data, storing data once, not twice, ordering, and a few other things. And so that means that when the cluster is in disarray and it needs to sort of reorganize itself, there's leader election going on, rebalancing, and a bunch of other things, it might be a while, especially after sort of a bigger crash, for all the data to be in sync again and for the cluster to be available for connections. Now, the reason Kafka does all that work is to maintain the guarantees that I discussed earlier. If you want the cluster to be there faster for you, you can do that by setting some of the timeouts and other variables that I mentioned on this slide, but at the cost of reducing those guarantees. So yes, the cluster is back faster. You can immediately start streaming in your data again, but there might be some inconsistencies in the data when you read it back. Now, this is, of course, an extremely great topic for engineers and to ponder about and to write code about and to worry about and to optimize, etc. And that's why Gwen Shapira, who is the manager of the Kafka performance team at Confluent, is giving me money to tell you that she is hiring. And so there's a job URL at the bottom of this slide. And so Gwen, I'll give you my Venmo, and you can transfer the fee for this advertising. After talking about scaling an individual Kafka cluster, I want to spend a few words about running Kafka in the cloud and scaling Kafka in the cloud. One of the businesses of Confluent is we run a hosted Kafka solution in the cloud. And so that means that instead of you running your Kafka cluster, we run your Kafka cluster for you. Running Kafka is not hard, but it's also not trivial. And you do need, data centers, hassle, Linux, failures, network, security. And there's a lot of, like running any IT infrastructure, running Kafka comes with responsibilities. And one of the things you can do is offload these responsibilities to us. We run your Kafka where you want it and where you need it at the service level that you requested. And you just tell us how many Kafka units you need, and we just make sure that Kafka is up. And so we run many thousands of large and small Kafka clusters for our customers. Now, running these Kafka clusters comes with some very specific scaling challenges. One of them is that you need to run each individual Kafka at a particular scale, but running a lot of these Kafkas together is also problematic. However, for you as a customer, you're relieved from all of these problems, and you get a UI and a CLI that you just have to deal with. And that works so well that we internally use our own UI a lot to make our own test clusters. And it's really clickety, click, 5 clicks, and you have a Kafka cluster, and you can start sending in your data. I gave you a screenshot on the slide of 2 of my test clusters that I created, aptly named cluster 1 and cluster _1, because even though we're very good at running Kafka, naming is really the next frontier in computer science. So what are the challenges that you need to overcome when you run many Apache Kafka clusters in the cloud? And I got 5 topics that I want to touch upon. First of all, there's some work to be done in Kafka itself. One of the ways in which we make running Kafka in the cloud for our customers a profitable proposition is that we can use, or you can ask us to run your Kafka in a multi-tenant environment, which means that we leverage the same set of machines for clusters of multiple customers, which obviously drives down costs because, typically a single cluster, especially if it's a test cluster, will not monopolize a set of brokers. And so by running customer clusters on the same set of brokers is just a very cost-effective way of doing things. However, you need to do some work on Kafka to make sure that these workloads don't interact with each other, that the multi-tenancy is safe and secure, and that customers don't see each other's data, etc., etc. The other thing to do is you need to wrestle with Kubernetes. The Kubernetes, for better or for worse, is the standard way of running things on the cloud. And so you need to sort of mold Kafka into Kubernetes pods and containers and stateful sets and daemon sets and all of the things that Kubernetes needs. And if you run a lot of them, that is a management problem in itself. And so one of the things you'll need to do is write a control plane to do that, and to do that in a way that meets service level agreements. So that means you need to do capacity management and these sort of things. One of the hardest topics, I personally think, in hosted Kafka or anything cloud is network access. I mean, obviously, we run the customers' clusters on the cloud provider's hardware, and that means they're basically on someone else's computers in the internet. And the question now becomes, how do you provide safe and secure network access to these things? Not every customer wants their data available on the internet or even reachable from the internet, even on top of SSL and API keys and secrets, etc. There's, of course, a very good use case to be made for creating a completely separate network environment. And that means that you need to wrestle with the cloud providers' somewhat Byzantine networking options, in order to create private networks and peer those or set up VPNs with the customers. That is quite a challenge, especially because of the sort of the very varied way in which cloud providers have implemented this, and all sorts of technical details that need to be just right in order to make all of this work. IP addresses, CIDR blocks, subnets, gateways, routes, public IP addresses, netting, etc. Thirdly, multi-cloud is a challenge. We run on the clouds of Amazon, Google, and Microsoft. The cloud providers provide more or less compatible features in terms they all offer Kubernetes, they all offer certain networking options, they all have, but compatible, and it does not mean identical. And there's lots of irritating differences between the cloud providers' offerings, especially around the topic of limits. Like how many nodes can you have to a Kubernetes cluster? How many pods can you have to a node? How many load balancers can you have per Kubernetes cluster? How many security groups can you have per node? How many security groups can you have per load balancer? How many? And so managing that environment and making sure that you still project all of these Kafka clusters onto the lowest cost service level agreement conformant infrastructure of cloud resources, that is like a huge challenge, and one that I'm worrying about on a day-by-day basis. And last but not least, obviously, security is always something to worry about. The internet is full of bad people that we need to protect our customers' data from, and that you need to protect your data from. Security nowadays, if you want my personal opinion, I'm not a security expert, but it's like an all-out arms race between the hackers and the good guys. And keeping up with what's going on and what is hip and happening in the attack world and how to defend yourself again, that is a challenge that everyone that's on the internet has to deal with. And so, yeah, if you run Apache Kafka in the cloud, that's something that you will have to deal with. However, it's not all terrible. There's also many great features about running Apache Kafka in the cloud, and that you can use the cloud provider's features to offer value for your streaming platform. First of all, like the cloud allows us to do multi-tenancy, and I mentioned this before, but it allows us to project multiple clusters on the same set of hardware and resources, thereby making it cost effective and also providing flexibility in terms of like growth and availability of capacity, etc. That is really a great feature. Secondly, cloud providers really have, if not infinite amount of storage, really a lot of storage, and we can use that in the event streaming platform to provide what we call infinite storage. All the data you send to a Confluent cloud, to Kafka run by Confluent, will be retained forever as long as like the cloud providers buy hard disks and you and we pay the bills, then everything will be all right and all your data will be stored for all eternity, which is really great for auditing and compliance. And personally, I'm developing a laptop backup program using Kafka as the backend because infinite storage streams, like what could go wrong? Thirdly, cloud providers are available in many different geographic regions, and so that allows you to create clusters close to where you are or to where your data is or where you think it needs to be. And these regions themselves are fairly advanced sets of data centers that span multiple failure domains, and this allows you to create clusters where they need to be and where they are, to create them in failure domains so that whatever happens, there's always enough capacity around to keep your cluster running. And so this is great for uptime and availability of the cluster. So parting thoughts, like I said, I can talk about this for hours, but we only have a limited amount of time. So there's two parting thoughts that I want to share with you. Like one of them is that I think these are great books. That's a parting thought. And you can have these great books too. There's a URL on the slide. If you go there, you can download these for O'Reilly books. And one of the reasons I appreciate these books is that they're extremely technical. And so they really provide great in-depth information on how Kafka works and what you can do with event streaming at the core of your IT architecture to keep data in motion, as we say at Confluent. The other thing I'd like to share is that Kafka is obviously a very interesting and fun and technically exciting project. And so I would like to invite you to join us either over at Confluent using the URL on the left, or the Apache Kafka community at large with the URL on the right. This is all from me right now. I would like to thank you for your attention. I would like to invite you to attend the Q&A and ask me questions. And if not, mail me. My email address is at the start of this presentation. Thank you very much for your attention.